So today we are going to discuss on uh, point defects. Uh, we have started discussion on crystal imperfection in the last lecture. There we have discussed on the different void spaces and the basic introduction of the solid solution. Now, the crystal imperfections, there are different kinds of crystal imperfections. We have discussed earlier also that there can be point defects or line defects or surface defects or volume defects. But one of the surface defects is very obvious, and definitely you can um, observe it very easily, that the external surface of any crystal is an obvious defect or imperfection. So let us try to understand this first. If you see different metallic materials, they having certain specific finite size. Okay, finite size. So if you look at the size, then definitely you can see there is a upper surface. Okay, so there is a surface of the body. Now, see, actually this material having certain crystal structure, and you know the definition of the crystal structure is that in the space lattice, uh, the lattice points having certain group of atoms which are called the basis. Okay, and then the crystal structure formed, and this repeating pattern is there within a crystal structure. But it is clear that the lattice is basically in infinite space, but definitely a particular object is not an infinite in size. So definitely it is clear that at the surface, if you look at the surface lattice points, the atoms which are there at the surface, they are not surrounded by the atoms exactly in a similar fashion if you compare an atom inside that particular body. So if you consider this is a body, and let us consider this is one of the atom, and you know that in case of a ideal crystal structure, each atom having identical surroundings. Okay, so these atom may be surrounded by few atoms like this, but if you consider one atom at the surface, so definitely on one side maybe you will get the similar kind of atoms, but definitely on the other side there is no such atoms, okay, which are it is bonded. So definitely the pattern or the similarity is not hold at the surface atoms. So that is why the surface are definitely a kind of imperfection. So that is why this particular line is very important, that external surface of a crystal is an obvious defect or imperfection. Okay, so this is the first thing, and definitely this is a kind of a surface defect. Why this is a surface defect? Because these defects occur throughout the surface, outer surface of the material which is made of some crystal. Now let us again remind these points that we have discussed earlier, that imperfection by their presence increase the energy or enthalpy and also the configuration entropy. So if some imperfections is there within the crystal, whether it is a point defect, line defect, surface defect, whatever that may be, if some imperfection is there, that definitely increase the energy, because just now we have seen the surface defect. So if you see, this is the point, one of the atom at the surface, so this atom is connected with another atom, suppose here, but it is supposed to be connected with another atom here, but since it is the outer surface, so this atom is actually not present, so this bond is actually not there. So that is why the corresponding to that bond energy, half of the bond energy will increase, and that means the energy of this atom will be higher. So this is not exactly at its most stable state. If you can remember the basic energy diagram, so where if this is the corresponding bond length where the energy is minimum, so definitely this bond is not present there, and that is why the corresponding energy level is higher. Okay, so definitely the atoms which are at the outer surface having higher energy. Okay, so that is not at their minimum energy level, that is respectively at a higher energy level. So you can understand that if imperfection is there here in case of a surface atom, which is imperfection because some of the bonds are missing, like these bonds are expected but not there because it is at the outer surface. So because of that, some energy has been increased. Similarly, within the material, you can also think that if this is the normal distribution of the or arrangement of the atoms, and if suddenly one of the atom is missing, like vacancy is created, so this atomic bond will be missing, and maybe the distance between these atoms will be much larger. So definitely the energy associated with this vacuum will be higher. Okay, because these atoms will have the higher energy. Okay, because you know that at only at a particular length, bond length, you will get the minimum energy. If the distance between them is increased, in that case also energy will increase. If the distance between them is decreased, in that case also the energy will increase. Okay, only at a specific bond length the energy will be minimum. So it is clear that if the imperfections are present, then definitely the energy will increase. This is the first part, that the increase in energy is associated with the imperfection. That may be reflected in terms of enthalpy or the energy. And another one is the configuration entropy. That will also increase. Configuration entropy will increase because other kinds of species are coming into the picture because of the imperfections. Maybe it is a vacuum or some other kinds of imperfections. So if that is another species, then it is very important that there are certain atomic sites within a material, and in them, suppose there are n number of atoms, but out of them maybe few atoms are missing, like vacuum or the vacancies. Okay, so let us consider there are n number of atoms which are not there. So this is definitely kind of imperfection because some of the atomic sites do not have any atom. This is a kind of crystal imperfection. So in that imperfection, you can understand the atomic arrangement out of these n atomic sites. Out of these n atomic sites, only n number of atoms are vacant. So how many different ways these vacant places can occupy in the whole region? So that can occur in n ways. The combination. So total number of atomic sites are n, and out of them n number of position can be arranged in a different way. This is what is the different possible randomness associated with the arrangement. Okay, so in this way you can find out the total number of configurations that is possible because of that particular species present. Here the species implied that it might be some impurity, it might be vacancy, so different kind of imperfections, crystal imperfections it may incur. So W, the number of configurations possible, is basically NCN, which can be calculated like n factorial by small n factorial into n minus n factorial. Okay, so in this way you can find out the total number of configurations, and you know that the associated configuration entropy, the definition, if you remember, of the configuration entropy is the Boltzmann constant multiplied by ln number of configurations possible. So K is Boltzmann constant into natural logarithm of W. What is W? Number of configurations possible. What is number of configurations? That is equal to like this. For this particular example, if there are n number of total atomic sites, if there are n point defects are there, suppose. Okay, so they can be arranged in a different, this many different ways. So W is the number of possible configurations. Okay, so in this way you can find out the configuration entropy. Okay, so if imperfections are there, then two things happen. One is that energy will increase, that is the first point, and second one, that configuration entropy will also increase. Okay, so this is the thing that you have to remember. Next, you see, second point, this means that by their presence, imperfections alter the free energy of the crystal. So if you remember the definition of the Gibbs free energy, which is basically the enthalpy minus T into S. Okay, so the free energy expression is this, and by the time you have understood that if imperfections are there, then H will increase and configuration entropy will also increase, because configuration entropy is a part of the thermal entropy, is a part of the total entropy. Okay, so both H and S will increase. So the second point tells that this means that by presence of the imperfections alter the free energy of the crystal, so free energy will change. Okay, now this third point, these then are in thermodynamic stable equilibrium if this lowers the free energy. So ultimately you have to see whether, because of these two changes, whether the overall Gibbs free energy is decreasing or increasing. If it is decreasing, then it will be stable equilibrium. Okay, if it lowers the free energy, that is a favorable situation, and if it increases, then that is definitely is not a favorable situation, that is not a stable equilibrium situation. And in that case, the impurities, if they are present somehow, and because of that, if Gibbs free energy increases, so whenever they get a chance, they will try to get out of the crystal. So otherwise, these are not in stable equilibrium and would like to get out from the crystal all the time, because they are not in a stable condition. So if they get any chance, they get a chance means if you give some kind of external energy in the form of mechanical energy or the thermal energy, they will try to get out of the crystal. Okay, so these are very, very important points, and that is true for any kinds of imperfections. These are true for any kinds of imperfections. So these are the different kinds of imperfections we are going to study. So first we'll take up the point imperfections, okay, and then we'll take the line and the surface imperfections. So point imperfections. So point imperfection means it is a imperfection associated a region around a point of maybe 1 to 2 atomic diameter. 1 to 2 atomic diameter. Okay, not more than that. If this volume that is associated is respectively larger, then it will become a volume defect. But we are considering it is in the range of 1 to 2 atomic diameter around the point. If that region is affected, it is a point imperfection. Now, point imperfections can be of different kinds, and we'll try to look at these in terms of our basic kinds of materials that we have studied. The basic kinds of material, if you remember, the main three kinds of bonds are present, primary bonds present in the material, like metallic bonds, and the materials are the metals, covalently bonded materials, and the ionically bonded materials. So separately we'll see that for this kind of materials, what kind of different point defects occurs. So in case of metallic structure, means the bond is the metallic bond, and in case of metallic bond, you know that each of the atoms are not always fulfilled with its electrons, and that is why electron pool is created. So everyone is sharing their valence electron throughout the material, and those shared electrons are shared with the other, and at times they are trying to fulfill the outer orbit, okay, of the atoms. So it's a kind of as a whole sharing throughout the material. It's not a localized sharing, okay. So in this kind of structure, in this kind of metals and alloys falling under this kind of bonded structure, you will find that vacancy, substitutional impurity atoms, interstitial impurity atom, and self-interstitial. These are the important different kinds of point defects you will find. So let us see one by one. In case of metals and alloys, so we are now discussing metals and alloys. Generally, in case of metals and alloys, you will find this kind of point defects. So by the time you have understood that what we mean by vacancy, vacancy means from a regular atomic site, if one of the atom is missing, that is called vacancy. So vacancy is possible in case of metals and alloys. And you see that substitutional impurity atom, already you know what is substitutional impurity atom. If one of the parent atom is substituted by some solute atom, then it is called the substitutional impurity atom. And that substitutional impurity atom can be larger than the parent atom, or it can be smaller than the parent atom. Okay, so the first one is the vacancy. Second one is a substitutional impurity atom. Okay. The third one is the interstitial impurity atom. You know that within the crystal structure there are interstitial void space, and if the atoms go into the interstitial void space, then that particular defect is called the interstitial uh, impurity. Okay, or interstitial impurity or interstitial imperfection. So here you can see a different kind of atom that is occupying a interstitial void space. Okay, so that is there in case of metals and alloys, and the reason is that you can think in that way, that uh, in case of metals, you know that all the atoms you can see here, all these atoms, they are not always fulfilled by their outermost orbit. The electrons in the outermost orbit are not always fulfilled. Okay, so they always try to get electrons so that the outermost orbit will be fulfilled, and for that they actually collect electrons from the pool where the electrons are available from the different valence electrons, so everyone is sharing. So that is why when some other interstitial impurity atom is trying to share their electrons, they are sometimes welcome. Okay, but definitely if the size of the atom is very large, in that case there is a chance that the compression of the electron clouds, so definitely some kind of strain energy will be developed if the size of the atom is large. But it is not but this kind of impurity is possible in case of metals and alloy. Self-interstitial or interstitiality imperfection is also another kind of point defects observed in metals and alloys. You can see in the interstitial void space. In the interstitial void space, the same atom of the parent atom is trying to occupy that place. Okay, so definitely this is a kind of imperfections, because a regular pattern will break if an atom is trying to go into the interstitial void space, and definitely lot of strain energy will be developed, lot of energy will be developed, because definitely the void space is very small. You know, in case of closed pack structure, you have seen it is only 22%, 44%, like that. So in that region, if a whole 100% atom is trying to get, so definitely it will strain the surrounding electron clouds. So definitely self-interstitial, the chances of making this kind of defects are less, because a lot of strain energy will increase. So there is a very rare chance that this kind of defects will occur, but it is still possible. And if it is possible, that is only possible in case of metals and alloys, not in other kinds. Okay, that you have to remember. So these are the different kinds of point imperfections possible in metals and alloys, you have to remember. Okay, so we have seen that in metals and alloys there may be vacancy, there may be substitutional impurity atom, there may be interstitial impurity atom, or it can be self-interstitial. Now coming to the covalently bonded material structure. In case of covalently bonded material structure, you may get vacancy, you may get substitutional impurity atom, but you do not get interstitial impurity atoms or the self-interstitial. The reason is very obvious, that in case of covalently bonded material, you know that what happens in case of a covalently bonded materials, they are strongly bonded by the localized sharing, right? They are sharing their electrons, and ultimately they are fulfilled with those electrons. So the atoms do not have do not require any further electrons from the outsider. So that is why they do not allow other impurity atom. They do not require any other impurity atom that will share their electrons, because they are already locally shared between two atoms. They have locally shared and they are fulfilled by their outermost orbit. They are quite stable now. They form like sp3 bonds, they form. Okay, so this kind of sharing is now in their void space. If some atom is going, though definitely that is not welcome at all, because they are not going to help anyway in that particular structure, because they are already fulfilled by their electrons in the localized sharing. So this kind of interstitial impurity or self-interstitial, this kind of imperfections are not observed in case of covalently bonded material. But definitely the vacancy may be present. But again, if the vacancy is there, then definitely a lot of energy will be required, because you know that to create a vacancy, a huge energy is required, because the sp3 is a very strong bond, very strong primary bond. If to break that sp3 bond, so it requires a lot of energy. So hardly you will find vacancies in case of a diamond. Maybe you require more than 2-ton 3-ton diamond to get a single vacancy. So it is not that vacancy is not present, it's rare, but still vacancy is very much possible in case of covalently bonded material. Substitutional impurity atom are rather very much common point defects in case of covalently bonded material. As you know, in case of silicon, germanium, which are basically the semiconductors, are covalently bonded, right? And you know, to make it more effective semiconducting effect, you know that boron or the phosphorus, this kind of doping is done to make it n-type or p-type, you know. So in that case, basically what is done, these impurity atoms or the doping, when it is done, it is nothing but the substitution impurity which is added. Okay, so in case of covalently bonded material, rather substitutional impurity is much more common. Excuse me. So these are the different kinds of point defects that we get in case of metallic structure, in case of covalently structure. Remember, in case of covalently bonded structure, we do not see interstitial or the self-interstitial point defects. Okay, only vacancy and substitutional are possible. Now coming to ionically bonded material. Now, ionically bonded materials like different kinds of ceramic structure, okay, those are ionically bonded material. Now, in ionically bonded material, excuse me. Now, ionically bonded material, the point defects that, which are observed are schottky imperfection, frenkel imperfection, substitutional impurity ion, cataion vacancy, and interstitial cation. Let us see all these kinds of point imperfections one by one. Rather, this is the ionically bonded material structure. The point defects are more common point defects are frenkel and the schottky imperfections. Remember, in ionically bonded materials, the atoms are joined by the ionic bond, where the cation and anion, you know the structure of sodium chloride, sodium plus and the chlorine minus, they form a particular molecule. This is a particular what we call a basis that is there basically in lattice points. Okay, so in this way the crystal structure actually created. So here in this diagram you see the cations are the smaller one, the red ones are the cations, and the anions are the larger ones which are negative. Okay, now first see the schottky imperfection. The schottky imperfection is that from the whole structure, if one cation and one anion is missing, then definitely the whole structure will still be electrically neutral. Remember, ultimately the whole material has to be electrically neutral. So if one cation is missing, then definitely one anion also has to be missing, so that it becomes electrically neutral. Okay, so if one cation is missing, and may not necessarily the another anion close to that is to be missing, it can be some other places, as you can see in this diagram. So if one anion and one cation is missing from the whole structure, then it is called a Schottky imperfection. It's a point defect, occurs in case of definitely ionic crystals, and it is not actually one cation one anion, it is basically one formula pair that is required. In suppose it is a sodium chloride, you can understand, okay, one sodium plus one chlorine minus, those are missing a particular pair, it's okay. But if it is a calcium chloride, okay, so in case of a calcium chloride, you know that the one calcium actually making bond with the two chlorine. So in one lattice point, the basis consisting of one calcium and two chlorine. So to make it electrically neutral, if one calcium is missing, so two chlorine has to be missing. By Schottky imperfection, what we mean? Basically, one formula pair will missing, so that the whole material, whole structure will be electrically neutral. This is what is the basic meaning. It's not that one cation, one anion. It is basically one formula pair that is to be missing, so that the structure will be electrically neutral. Okay, so this is what is the Schottky imperfection. Now coming to the Frenkel imperfection, this is again we see in case of ionic crystals only, and this is again a point defect. And here you see that one cation is missing from its regular site, and it is going to some interstitial void space. Here you see at this regular site the cation is missing, and that cation may be occupying some interstitial void space here. Okay, so in this way it is there still within the whole material, and that is why electrical neutrality is still okay, no problem with that electrical neutrality. But this kind of defect is called the Frenkel defect. So I think this is clear that what we mean by Schottky imperfection, one formula pair is missing, so that the whole structure is electrically neutral. And Frenkel defect, one cation is missing from its regular site and occupying some interstitial void space, some other place. Okay, so this is what is the Frenkel defect. So Schottky and Frenkel, these are two very important point defects in ionically bonded structure. Now after these two, what is the next one? Is a substitutional impurity atom, impurity ion, cation vacancy, and interstitial cation. Let us see, these are the other kinds of defects occur in case of ionic crystals. So ionic crystals, always you will find cation and anion. As you can see, the smaller ones are the cations and the larger ones are the anions. Now you see that three kinds of defects has been shown here. One kinds of defects, let us try to understand first, that is the cation vacancy. You see that cation vacancy. So cation vacancy is a kind of defects. Now let us first try to understand how is it possible that from its regular site, one of the cation is missing. This is what is the cation vacancy. Cation vacancy means is very simple, that in the whole structure from its regular site, one cation or few cations are missing. This is what is the cation vacancy. Now can you tell me that how is it possible that one of the cation will be missing but still the whole structure will be electrically neutral? How this is possible? How is this possible that one of the cation is missing but the whole structure will be electrically neutral? Suppose only cation vacancy is there, so from its regular site one cation is missing, but still the whole structure will be electrically neutral. How is this possible?
স্যার ক্যাটায়নটা স্যার ওই এটার স্ট্রাকচারটার মধ্যেই আছে, শুধু জায়গাটা শিফট করে নিয়েছে।
No. That is not a cation vacancy. That is a Frenkel defect. If the cation is missing from its regular side and taking some other place in the structure, then it is a Frenkel defect. But cation vacancy means It is not at all there within the structure. Nowhere in the structure that particular cation is there. Only one of the cation is missing from the structure. Let me show you. Just look at this portion of the diagram. Suppose this is the whole structure we are showing. Let us
স্যার আর
consider.
একটা অ্যানায়ন ভ্যাকান্সি থাকলেই তো নিউট্রাল হয়ে যায়।
Yes.
আর একটা অ্যানায়ন ভ্যাকান্সি থাকলেই তো পুরো
No,
এটা
no, no.
নিউট্রাল
Anion
হয়।
vacancy nahi. Anion vacancy nahi. Anion vacancy is the different kinds of defect. Let us consider the cation vacancy is only there. Let us consider only cation vacancies there. Let us consider this is the thing, and only from its regular side, one of the cation is missing. Only this is the crystal condition. That's all. So from its regular side, one of the cation that is missing. You can see here, the cation is missing. Cation is not there. But still it is electrically neutral. If this kind of situation occurs, then it is called cation vacancy. Anion vacancy means the whole thing is exactly similar to here, only one anion is missing or maybe few anions are missing, but thing is exactly like this. No other things are there. Actually in this diagram you actually confused. You are trying to consider that all three different kinds of defects and trying to consider that whole thing is neutral. No, it is not like that. Only suppose only cation vacancy is there, no anion vacancy is there, no cation interstitial is there, nothing is there, only cation vacancy is there, but still it is electrically neutral, then that particular defect is called cation vacancy. Like what I have trying to show you in this diagram. This is what is cation vacancy. So at this place the cation is missing, but still it is electrically neutral. Let me tell you that how is this possible. So let us see let us take one of the example, then you will understand it better. Suppose I think that will help you to understand. In this diagram, suppose the sodium chloride is there. You can see this is the structure, sodium chloride, and you can understand the cation and anion. The cations are shown by blue, anions are shown by green. Now suppose you substitute one of the sodium by calcium 2+ ion. Okay, so if one of the sodium is substituted by calcium 2+ ion, in that case here you can see one of the blue sodium is substituted by calcium 2+ ion. So this is a kind of substitutional impurity. So this is the first thing that has occurred. Because of that, what happens, since calcium having valency 2, so it will actually create bond. It is equivalent to 2 sodium, because you know that each sodium requires 1 chlorine. So calcium 2+ requires 2 chlorine. So it will supply electron to 2 chlorine. So calcium 2+ will supply electron to 2 chlorines. So in that case, if you remove one of the sodium out of the crystal, still it will be electrically neutral, because corresponding to that sodium, calcium 2+ ion will supply electron to the chlorines. So in this way, the vacancy that will be created is cation vacancy. So in the cation vacancy, what is actually happening, one of the parent atom, that means one of the cation may be substituted by the higher valency some other atoms, other cations, and that is why it is possible to remove one of the regular sodium ion out of the crystal. Still the whole structure will be electrically neutral, and then in the structure you may find a vacancy in the position of a cation, but still it is electrically neutral, because one or other so one of the sodium atom may be substituted by the higher valency some cation. So this is what is called the cation vacancy. So when you are substituting one of the atoms, one of the cations, when you are substituting one of the cations with respect to higher valency, some cation, in that case, it is possible to get the cation vacancy. Clear? What is cation vacancy?
Yes, sir.
Okay. Now you see, if now in the similar way, if you try to think in that way, suppose one of the chlorine is substituted by the oxygen. If the chlorine is suppose substituted by oxygen, you know the valency of chlorine is -1, and if you substitute by oxygen, then it is possible that one of the chlorine is missing. So anion vacancy is possible. So it completely depends that kind of a substitution if occurs. In that case, either cation vacancy or the anion vacancy may be possible observed within this structure. So what we mean by cation vacancy, what we mean by anion vacancy, is it clear to you?
Yes, sir, clear.
Okay. Sometimes what happens in this case, another one you have seen like cataion interstitial. One of the defects was there. We have studied that substitutional impurity. And if the substitutional impurity ion is such that it is having higher valency, or in that case, it is possible that either cation vacancy or the anion vacancy will occur, right? That you have understood. If the substitutional impurity ion do not have the same valency as that of the which is it is substituting, in that case either cation or the anion vacancy is possible, but still it will be electrically neutral. Another one is there interstitial cation. Interstitial cation is generally observed in case of the situations of anion vacancy. You see here interstitial cation, suppose you are replacing one of the chlorine by oxygen. You are replacing one of the chlorine by oxygen. So oxygen is serving a purpose of two chlorines. So in that case, what is possible, one of the solution might be that one of the chlorine will get out of the crystal so that it will become electrically neutral. This is one of the solution, and in that way the point imperfection created will be anion vacancy. But another way that it can be electrically neutral if another sodium ion is present, extra sodium ion is present in the interstitial void space, because already oxygen is there, oxygen having capacity equivalent to 2 chlorine. So one cation can also make it electrically neutral. So that cation will be definitely extra cation. So that extra cation go into some interstitial void space. So that is what is called the cation interstitial. So in two ways the problem can be solved. One of the way is by creating anion vacancy. That means if oxygen is replaced one chlorine, then one of the chlorine has to go to make it electrically neutral. That will produce anion vacancy. Or if one of the chlorine is replaced by oxygen, in that case to make it electrically neutral, another sodium is required. And that sodium will go in some interstitial void space. So in that case, it is called the cation interstitial. Okay. So these are the different kinds of defects. So that is why this has been shown that cation interstitial is a kind of defect. Okay. Cation vacancy is a kind of defect. Anion vacancy is a kind of defect. So these are the different kinds of defects which are possible in case of ionic crystals. And definitely the most important defects in the ionic crystals are frenkel and schottky imperfections. Clear? Okay. Two examples are there. So these kind of problems you can expect in the exam, that when a calcium is substituted for a sodium ion in a sodium chloride crystal, then what point defects are possible? If it is clear that if calcium ion is substituted sodium plus, then definitely cation vacancy will be created. And the question is how many of these defects exist for every Ca2 plus ion. It is clear that since the valency is 1, so every Ca2 plus ion, that will be one vacancy that will be created. Next, you see for the second problem, what point defects are possible for magnesium oxide as impurity in Al2O3. So the basic structure is Al2O3, where aluminium having plus 3. Okay, now one of the aluminium plus 3 is substituted by magnesium oxide. That means one of the aluminium plus 3 is substituted by magnesium 2 plus. Okay, so definitely now the situation is you are substituting one of the ion which is having valency less than this value. If it is less than this value, then definitely the kind of defects that you can expect is that anion vacancy. Okay, you can expect anion vacancy will be there. Okay, or it can be cation interstitial. And to match it, it is clear that if you take two such defects, two aluminium 3 plus, that will corresponding to balance to 3 of that. So in that case, the one difference will be created. So in that way, you can find out that how many magnesium 2 plus ion must be added to form such each of these defects. Okay, so these are the kind of problems those are expected. So from your basic idea, if your basic concept is clear, then you definitely will be able to answer. Now coming to the quantitative calculation of the fraction of defects, fraction of point defects to be very specific. And fraction of point defects is estimated using this particular formula, that if ND is the number of defects by N is the number of total number of sites. So N divided by ND divided by N, this is what is the fraction of defects. So number of point defects divided by total number of atomic sites. So this ratio is equal to what? Exponential of minus of Q. That is what is the activation energy required to create that defect. Suppose that particular point defect is a vacancy. So to form a single vacancy, how much energy will increase? So this is that quantity. This activation energy means to create a single point defect, how much energy will raise in the material. Already we have discussed, if you create a point defect, that will increase the energy. So that amount of energy or the enthalpy that will increase is basically shown here by QD. So minus of QD divided by K into T. K is the Boltzmann constant and T is the temperature in the absolute scale. Okay, so K is the Boltzmann constant and T is the temperature in absolute scale. So this is what is the formula that you can remember. But the derivation of the formula is not very difficult. It's very simple. You can derive this expression also, but for your exam purpose, it is only required to apply this particular formula or the fraction of defects. And you can see the derivation also is not very difficult, but I am not going in much detail of the derivation, but I will show you all the steps of derivation. You do it in your copy, just following the steps. So first, you know that the basic idea is what we want to find out is basically how many number of defects will be there in thermodynamic equilibrium. So within a crystal, some defects may be there, and they will be there because they are in stable equilibrium. It is possible that in some of the defects will be present in stable equilibrium. Okay, but to find out that fraction, so how many defects will be there in stable equilibrium, that we want to estimate. Okay, where small n is the number of defects and maybe the capital N is the total number of atomic sites. Okay, so this fraction we actually want to find out. In thermodynamic equilibrium, what is the fraction of defect? We want to know that what is the fraction of defects. Okay, so if you remember, we have started with discussion that we know that the fraction of defects are very small, right? Fraction of defects are very small, but they having a great impact on the material properties. That is why we are studying defects. But what is that fraction of defects if we want to really estimate that? So let us try to estimate what is the fraction. We know that it is a very small fraction, but what is that fraction? So to do that calculation, let us see that the expression of the change of energy. Change of energy means if there is no defect and if there is defect, then what is the change of free energy? Okay, so that change of energy will be definitely the change of energy because of those defects. Let us take a very simple defect. Suppose vacancy. We are considering a vacancy is a kind of point defect. So for each vacancy, suppose the energy increase is EF. For each vacancy, energy increases EF. So if there are small n number of vacancies, small n number of point defects, then what is the total amount of energy increase? Simply small n into EF. That is the amount of energy increase. So you can see the free energy expression. The first part is the amount of energy change, and that will be n into EF. Clear? So n into EF is basically what is the amount of energy increase if there are n number of defects or n number of vacancies, minus T into S. Now this change of entropy is basically the change of configuration entropy. Okay, so what is the change of configuration entropy? That you have to write, and T is the temperature in absolute scale. This is what is the expression of free energy. We know it. So to find out this change of entropy, let us write the expression for the configuration entropy, and that we know is what? That K log of W, where W is the total number of possible arrangement. So already we have seen that what is W? This W is if there are total n number of atomic sites, if there are n number of atomic sites, and if there are n number of vacancies, then NCN will be the number of configurations. Okay, so here n defects and n atoms and n plus n lattice sites. Here the problem is bit different. That means what they have thought, they have considered that there are n defects. Okay, n defects, and total number of atomic sites is n plus n. That means they have considered that n atoms are there, are in places are actually vacant, and that is why the total atomic sites is n plus n. Then what will be W? Then for their case, the W will be n plus n C n. So out of the total number of atomic sites, how many ways these n vacancies can be arranged? Okay, so they can be arranged in this many number of ways. So you just write these quantities in factorials. So n plus n factorials divided by n factorials into n factorials. So this is what is W. Then you have to take the log of W. Okay, if you take log of W, in that case this n or small n, these quantities are very large quantities, because you know that even they are in the order of 10 to the power 23, 24, 25, like that. So they are very large quantities. So you can use the Stirling's approximation. If you remember what is Stirling's approximation, that x factorial log of x factorial is equal to log of x factorial is equal to x log of x minus x. So this is what is the Stirling's approximation. You can use this relation is true only if this x is very, very large, very, very larger than 1. In that case, you can use the Stirling's approximation, and which is true here. And so you have to calculate basically this expression of S. So if you do that, you see the expression of W, you see what is S, and then the Stirling's approximation has been used, and after simplification you are getting the expression of S. This is a simple exercise, you just do it in your copy. After that, the value of S and the total energy, that expression has been put here, and this is what is the expression of final change of free energy. So what we mean by thermal equilibrium? For stable equilibrium, we know the change of free energy will be where, which one is the variable? The number of defects. So delta G by del N, this quantity will be 0. So because the free energy will be minimum corresponding to stable equilibrium, so free energy will be minimum. So del N of delta G, this quantity will be 0. So simply differentiate this expression with respect to small n. If you do that, you will get this expression, and that is equal to 0 for the minimum free energy. Now next part is just you simplify it and you will get this expression. Okay, and n plus n, this quantity is exact almost similar to small n, because small n, the number of vacancies are actually very small with respect to the number of atoms present. So n plus n and n can be considered almost similar. So you just replace this quantity by capital N. So this will become n by capital N. Okay, so this quantity can be approximated as n by capital N, and that is equal to exponential of this quantity. Okay, so this is what is the derivation, that the fraction of vacancies or the defects that is present within the material. So this is the final expression. Now, what kind of problems are coming in your exam? Suppose the problem like this, that find the number of vacancies present in 1 meter cube of copper at 1000 degrees centigrade. What you have to do? You have to simply use this basic formula. You only have to remember this formula. So you have to find out, the question is, you have to find out number of vacancies. Okay, so here you can see the activation energy or the energy required for the vacancy formation, that is given here. In unit is very important. Here the unit is given electron volt per atom. So if it is given per atom, in that case, remember we use the Boltzmann constant. And if it is given suppose joule per mole, in that unit per mole, in that case, instead of Boltzmann constant, we'll simply write the gas constant, universal gas constant, because you know the Avogadro number into Boltzmann constant is equal to R. Okay, universal gas constant. So here it is per atom, so Boltzmann constant you just use, and temperature is given, converted into Kelvin. Okay, and you just put, you will get the fraction. And here from this problem, at least you can get some idea about the fraction of the vacancies present. It is in the order of 10 to the power minus 4. But 10 to the power minus 4 is a large number, not very small number, because the temperature is close to the melting point of the copper. Okay, if the melting point of copper is around 1400 degrees centigrade, 1000 degrees centigrade is very close. So at a very higher temperature, you see the fraction of defects are very small. But if you go to the room temperature, maybe 300 Kelvin, if you just put the value of 300 Kelvin here instead of 1273, you will find this order will change to in the order of 10 to the power minus 16. Okay, so such a small fraction is actually present as a defect, right, in the order of 10 to the power minus 16. So close to melting point, definitely you will get the fraction of defects are less, and that is in the order of this. Anyway, and so finally, if you have to find out the number of vacancies, you just simply multiply it with the total number of atoms, total number of atomic sites that is present. Okay, and total number of atomic sites you can easily find out, because you know that atomic weight of copper is given. So you just convert it to corresponding total number of atoms. Here you can see, and you just multiply it, you will get the number of vacancies. But the same question can be given in the SI unit also. So like this, exactly similar question, only it is 800 Kelvin. Same problem for the copper. You see, the same formula has been used, only the nomenclature is a bit different. Here delta HF, that is the same thing corresponding to each vacancy. This is the amount of energy which is known. So just simply put it, and since it is given per mole, so that is why you can see here, instead of Boltzmann constant, it is universal gas constant which has been used. And other things are exactly similar, and you can see that what is the fraction of atoms. You see the temperature is only 200 Kelvin less, and the fraction is in the order of 10 to the power minus 8. Okay, so and you see that if the temperature is close to 1350, at that temperature you see the fraction becomes in the order of 10 to the power minus 5. So you can understand that if you increase the temperature, the fraction actually decreases. That also is clear. So unit is very important. You have to remember some quantities like Boltzmann constant, but it is expected that it will be given in the problem. Otherwise, this is what about the point defects. Okay. So let me close it.